Now, the first thing which I found was, for instance, everybody was having a problem with these issues like reflexive closure, reflexive or symmetric or transitive closure, right? We did only these three, there can be others. Now, over here, the first thing that you must remember is a relation on a set A is just a subset of A cross A, right? Clear? Now,
Yes.
the set of all relations on A, therefore, is nothing else. I think I wrote this as set of all subsets, right? Which is the set of all subsets, or the powered set of A cross A.
Doctor, are you sharing the screen because we don't see it, or are you just talking?
Sorry, okay. So now, do you see it?
Yes, I can see it now.
Yes, we can see it now.
Okay. So, the thing is that it is the set of all subsets of A cross A. Now you know subsets can be compared. Subsets of a set, of any set, are compared by the set inclusion, which is this, which is almost like less than. So you know that we have already seen. So the way we have done it, we have seen that it is, so it is kind of a relation between sets. So it's a relation. So if you are looking into subsets of a set X, so on the set 2 to the power X, you are defining a relation which is say PQ belonging to 2 to the power X cross 2 to the power X, such that P is a subset of Q. Okay? So that is a relation, and this relation is, we know, it is reflexive, it is transitive, and it is antisymmetric. As well as we also know that there can be sets, can be P and Q, which are not related. Not related by this subset. So that means neither is P a subset of Q. And from Venn diagrams, you know that you would draw things like this. So P is neither is P a subset of Q, nor is Q a subset of P. We usually would write things like this. Okay. Now, and we have done other things also. Now, let's come to this So we are defining I think it's better to mute on your side. Uh, so some property, some set theoretic property. So over here we are looking into reflexivity of a relation. So reflexive means, so reflexive relation, reflexive R means R is a subset of x cross x, and x belongs to R for all x in x. Okay, so this is a property, this is a set theoretic property. Obviously every set, every subset of x cross x may not satisfy this property. Okay, now for instance, there was this question from Ayub whether you should take a union. Now, if something doesn't satisfy this property, how can it fail to satisfy this property? Well, sometimes it is a problem of excess, sometimes it is a problem of too little. That means here it is a problem of too little. That means, so R fails to be reflexive what does it mean? That means this is the same thing as saying that there exists an x in R. Sorry, there exists an x in the set on which the relation is defined, x, such that the pair xx doesn't belong to R. Right? Clear?
Yes. Yes.
So it is a problem of, so that means R can fail to be reflexive if certain elements are not there. So you have to increase R to make it reflexive. Okay? So the idea is that you have to increase, you have to make R bigger to make it reflexive. Okay? So how do you do it? Well, you will obviously then include all those x's which failed, which was not in, for all those x's for which xx was not in R, and therefore you add all of them. So if you add the whole of diagonal, now adding means nothing else but taking union, right? So if you do this, then this new relation R prime, say, or which I denoted as R with the this is obviously reflexive. Okay, and that is where actually we also observe that R is reflexive if and only if it contains the diagonal. Okay? So you see, you have to make it bigger, you cannot make it smaller. So now you see, if a relation is reflexive, then any relation which is larger than it is also reflexive. But if you make the relation smaller, well, it may fail to become reflexive. You should get this idea. Okay? All right? So this is reflexive. So this part is. So now this is a reflexive relation, and this relation contains R. So now I am saying that this is the smallest one. So what do I mean by this? That suppose S is a reflexive relation and S is larger than R. I am giving it. So then, since you have told me, since it is reflexive, it already tells me this part is equivalent to saying S contains the diagonal. And therefore, from this and this, this implies, these two imply that S contains this. That you know, if A contains B and A contains C, then A contains B union C, which is your. So this is saying that amidst all reflexive relations which contain R, this one, R ref, is the smallest one which contains. So do you get it now? What do I wanted to ask or assert by saying the smallest? Right? Is it clear?
Yes.
So in the same way, so suppose R then I am saying this is symmetric. This is the first fact. The second fact, so in doing such things, you have to show, what do you have to show? You have to show that it is symmetric. Then you have to show that this is bigger than R, which is trivial because you have added something to R. And finally, if S is symmetric, so something which is having both these properties 1 and 2, and S is a subset, S is a superset of R, then you have to show that S contains this. Right? So that's, if you can show this, then you can say, so do you get the feeling? How do you say that something is the smallest with this property? So R sim is the smallest equivalence relation on X which contains R. So you have extended R to make it symmetric. Again, you see, this is the failure of a symmetry again is a problem of little. Why? Why is it? What do you mean by symmetry? X R Y implies Y R X. So how does R fail to be symmetric? R is not symmetric. This means, so this is symmetry. So this means that this statement is false. That means there exists an x and y in R such that x are y, but this doesn't hold, but and y are x doesn't hold good. Okay? So xy is in R, but yx is not. So you see, it fails to contain some. So you have to put in those things. You have to inject those extra things to make it symmetric. Okay? All right? So I leave it again to you. Again, the transitivity you can. So let me write it down for sake of completion again. So R. So what is transitive? It means that x, r, y, r, z. Remember, these are two statements: x, r, y, and y, r, z. This simply implies this. So, not transitive. So from now on, whenever you see a property, the first thing is to not only to analyze it, first check what does it mean, whether it is an implication statement, whether it is an assertive statement or whatever. It might have many components like that. But always then to find, the next thing is, when does it not satisfy it? So find an example, not only an example of something which satisfies it, and when does it not satisfy it? Both the ways you must see it. So this statement is false. So that means again, there exists x, there exists a triplet now. It says that x, r, y, r, z, and x, r, z doesn't hold. Okay? So again you have to find out, take all those triples for which this is failing and inject them in. But the problem over here in this case is, here it is a kind of a it is a process. So on the first level you find a triplet x, y, z, so that x and y are related, y and z are related, but x and z is not related. So you put that xz in that. Very well. But then suddenly you find, since you have put that xz down there, then there is xz sitting over there, zt also sitting over there, but xt is not sitting over there. Okay? This problem strangely doesn't arise in the previous two cases, because it was just, it's just a magic or an accident that now, since this third party comes up, there is a possibility of few other options. So possibly it was, so I often, for transitive relations, I think I wrote in someone's paper assignment, I often write it like this. If x is related to y, I write it like this. And if it is this, so this arrow is missing. All right? But there was already some arrow like this. Now you introduced this new arrow to make it transitive, but then you see that this arrow is missing now, so you have to introduce this one. Then possibly there was a fourth one. And that's why this process doesn't stop in one stage. And this is only for one starting thing. There could be several others. So that's why this brings in your stages. So that's how you get hold of your RNs. So first you take R, then you take R composed R, which is the composition level is this blue arrow. So that is X, Z, that is in R composed R. Then you take in R composed R. So let me better write it like this, since I drew this one in black, and then possibly further one. So and you carry on, and you carry on and on like this. Okay? You carry on and on like this, and it turns out, well, this is where the axiomatic system will help us understand later, but here, as I've said, we have taken for granted these natural numbers. So we take this union. So R union R composed R union R composed R composed R. So union of all of these possibly. These are of length n, and so on. Okay? And this was what I wrote as R star or something like that, I don't remember. This is called the transitive closure of this. And then you take its, so you take the transitive closure of this. So that's the transitive closure of this. So that's the, why I write it like this, I have already said R tran, right? So what do you have to show? You have to show that R trans is a transitive relation. Then you have to show that R trans contains R, which is immediate. And finally, you have to show that if S is a transitive relation, containing, so transitive relation S this, then okay. So that says then that R trans is the smallest one. Okay. So we will see again and again that whenever we make such constructions, so these constructions, we can think of it as removing a defect. The defect was that it was not reflexive, or it was not symmetric, it was not transitive. That was the defect. To remove it, to make it better, to make it good looking, so to make it reflexive, or to make it symmetric, or to make it transitive, okay, we will provide several such constructions. Even later on we will see as we go on. But we are just not interested in one construction, we are interested in the best. And what do we mean by best is something which we are going to make clear as we go along the path. In this case of relations, the best means, since we saw the deficit was of absence, was of too little, so we have to make it bigger. So the best means the smallest one larger than it. Okay? Is this now clear? On what you have to do and so on?
Yes, it is now. Thanks, Doc.
Okay.
Yeah, yes, Doc, it's clearer now.
Okay. So that exercise is left. Now let's come to your questions about functions. So section 5, you have the notes with you right now, right? So you got hold of the stock diagram. That's a very intuitive picture which we will utilize again and again. So do you have any questions up to, say, remark 5.8? Yes?
No.
So that part is...
Myself also, no, yes.
So it's clear, right? And you see the over here, I drew those functions, sine and sine 4a and 4b, just to illustrate that unfortunately in many recent books I find this a problem, that functions are not properly dealt. So remark 5.5 is, which should have been something which was very, very clear from the start, but there is we usually look into the rule, the formula for the function, and if the formulas are same, we say the functions are same. But that's not the case. And as you see, the graphs of the functions are completely different. So that should suggest, that should have already made you ask the question even in that class, that if the graphs are different, why would the functions be same? Okay. So, and that's exactly the picture. So functions are equal. So function encodes, every function comes with 3 pieces of information. One is its domain, the second is its codomain, and the third is the rule. The rule is actually the graph. This graph is the rule because these are the points xfx of the type xfx, right? So the graph, what you draw is the rule. Okay. Now there is also another common fact, common, how do I say, a common expectation that whenever I give you a function, you must tell me what is y equal to. So you must give me a formula for that function. Now, okay, if I wanted to be very cheeky, I would have said, well, if look into remark 5.3, when I write that unique element y is alternatively written as fx, or x maps to fx under f, or f colon x to y, or x goes to fx. So I could, if I am really cheeky, I would have said, well, y equal to fx is the formula, but we will still not be satisfied with it. Now this is actually a very, very subtle issue, to expect that every function should have a formula, and you mean a kind of a formula like y equals sine x, or y equals cos x, or y equals x squared plus 2 times sine x, or something like this. Now this, not only people who like you who are new to this formal treatment, or even very established mathematicians like Lagrange and others had this problem, that every function should have a formula. But when it was established that there are several functions which do not have a formula like that, there was a big row, and we will see that having a formula in that old way is not right. Rather than we should always think of it that it is a graph, the rule which is being just given whenever we say that f is a relation. Okay, so that's the other way of looking into this problem. And then there is I was thinking whether I should write a small historical note about this, but it would make it very long, so I didn't write it. But at some point I would include this, that this formulas for functions is a big it was a big deal at one point of time, and the set theoretic approach actually made it very clear. Okay, so now let's the set of all functions I'll denote by like this, or as I said already, I like this hom AB kind of a symbol. Okay, now let's come to this types of functions. Yes, number one, identity function. There should not be any question about it, right? That's quite clear. You have a very clear formula for that function even. 1ax is equal to x, right?
Yes.
Okay.
Yes.
Now, someone asked me a question about f composed 1a. So, this prove this. F composed 1a is f and 1b composed f is f. Any questions about that?
Not on my side.
Okay. See, composition must not be any problem, because we have already done composite relations, right? And I have shown in remark 5.7 that same composition of relations is actually the composition. So over here the diagram is like, so you are coming from A to A by 1a, and then using f. So f composed 1a means if you apply it to an element x of a, 1a of x is x, and so fx. So, okay, so that should not be. Now let's come to number 2, inclusion function. There shouldn't be any problem with it. Only the fact is the formula for the function looks to be the same as identity, but it is not the identity. Okay? So 1 and 2 should make it clear that on that question on equality of functions. Okay? Clear?
Yes.
Okay. Now let's come to 3. So, any problems? The first part of 3. First, let's look into the first paragraph of 3. Any problems?
Not on my side.
Anyone else?
I don't also have a problem with this.
Yes, you don't have a problem on that, right? It was Charles, right?
Yes, Doc, it was me.
Yeah. Okay. Now let's come to the second part of the story. Any problems with that? So I have taken this set. Now there are these projections, product projections. You know what they do. So it takes, the members of A cross B are often written like these pairs. I was writing them like this. This is taken to the second coordinate and this is taken to the first coordinate. Okay? Now I have given you another information that there is another set T and there are two more functions. One I have told FA and one I have told FB. Now think of it. What is happening? You take T over here. What is happening? Well, FB takes you to this element FB of T. And FA will take you to this element FA of T. Right? Now, given these two elements, can you think of an element of A cross B?
F of IT.
Correct?
And for the B, F of BT.
Correct. So that ordered pair. Right? This ordered pair. And what does the projection do to this? It obviously takes this pair to this and the projection takes you to this. So now you are bothered with this assignment from T So the fact is whether this is going to define a function. Right? So that is the question, whether this is a function. Now let's try and see. Firstly, for every t, what do you have to check? For every t there is something over here. Yes, I have given that assignment. For every t in t I have given this assignment. Good. Alright, that's the first one, remember? So it's a relation. So if you have to be really very, very pedantic, what you are doing is you are taking this relation. So this is obviously a subset of, so it's a relation, right? Correct? Secondly, the way you have defined it for all t, right? That's also right, correct? because you will take U to be FAT, FBT as you say. Alright? Clear? Yeah? Now
Yes.
now suppose TU and TU prime both belong to F. Okay? So then you know, suppose you have to show U is equal to U prime. So U is something like this. U is FAT, FBT, and says let me have U prime is okay. So since both of them are here, since FA and FB are functions, so this tells me, so therefore T FAT and T and U1 prime, they are in FA, and T and FBT and T and U2 prime are both in FB. So this forces U1 prime must be FAT, and this forces U2 prime must be FBT, because they are functions. And from here, therefore, U is equal to U. So this is a function. Okay? So this is a complete pedantic proof. In the initial stage, you should actually go through and write this proof. But as you go on, you will see that this is getting pretty clear. You can see it from, since FA and FB are functions, for each T you have a unique choice of FA and a unique choice of FB, and hence a unique choice of this pair. Okay? So F is this function. Okay? So I have defined a function over here, and as I have observed that PA composed F is nothing else but FA, and PB composed F is nothing else but FB. Okay? Now, there is this second part of it. There is only, it says, a unique function. So, firstly, so first part is I have established the existence of a function. So now the next question is, why should this F be unique? What does it mean? You have to, I am not saying that there is one and only one function from T to A cross B. I am saying the statement is uniqueness. F is the only function such that if PA composed F is equal to FA and PB composed F is equal to F. So that's my whole story. So let me draw this diagram again. Okay, so this is the story. So that is what I am saying. So you see now here it comes that commutativity and so on, but we'll go to that feature next. So how do we show that? So let, if possible, so let there be another. Let there be another one G. So let be a function such that if A is equal to PA composed G and if B is equal to PB composed G. So I have to show that F is equal to G. Now already you see F and G have the same domain and the codomain. So to prove equality, so F and G have already the same codomain and domain. So we should only show, so it remains to show that if T is equal to GT for each T in T. Right? Clear? If I have to show that they are equal, if I show this, it is enough, right? Clear? Yes or no?
Yes, Doc, yes. We
Yes,
understand.
yes.
Okay.
Clear, Doc.
Now, so how do you show this? Choose and fix a T from T. Now let me look into what is GT. So let GT, it's a pair, so it looks like some AB for some A in A and B in B. Right? Now, let me apply these rules. So, FAT is equal to PA of GT, which is PA of AB, which is A. And similarly, FBT is PB of GT, which is PB of AB, which is B. So A is equal to, so therefore GT is equal to AB is equal to FAT, FBT, and this is nothing else but your FT. So you see, you cannot have any other way. So you have only exactly one way of doing this. Okay? So does this give you a proof? So is this clear now? So
Yes, it is, Doctor.
so
Yes, it is.
there was so this little bit, there was a lot of things to actually write and understand. Okay, so we will come across with these kinds of diagrams and utilize these diagrams again and again and again. Okay, now I'll just show, somebody asked about how do you use the commutativity. I'll just quickly then show number 4. So let's see. So what did we show? So now what is it? We have A to B. So okay. So we have now, sorry, so this is the initial thing, right? Now forget, it is just like another thing. You have to now look into this composite. What is it? F composed PA and F G composed PC. So you have this picture, you have this, see what did you do? The picture is like this. You have something over here, A cross B, two arrows going out, and whenever from something you have two arrows coming to these same endpoints, you can fill this part uniquely, right? This special thing, this is something very special. So if I write this, if I redraw this diagram like this, so this is something special I am not writing, that is your A cross B. And whenever you have two such things, there is one and only one way you can fill this diagram going to this. So your end point is this, right? That is what it is saying. That is the meaning of this diagram, right? Let's try to look at it in this way, okay? So, coming back, if I look at it in this way, look at this. You have B cross D, that special thing given. These two are the projection maps. From A cross C, you have two maps coming into B and D. So there can be only one way. There exists only one way to complete this diagram. And what is the equation? PB composed H must be equal to F composed PA, and PD composed H must be equal to G composed PC. So now let me try and see what is so. Okay, I have got hold of this function. Now the next question is, how will I get to know what is H of, say, AC? Where is H of AC going to? How will I know this? Well, I have to know H of AC. Okay. So this will be something. Okay, this will come to some B and D over here. What is B? B is nothing else but PB of BD. But then you have told me this is nothing else but PB of H of AC. Now you see, I am going to utilize these equations. PB composed H is nothing else but F composed PA. Okay? But then PA of AC is nothing else but A. So B is nothing else but FA. And similarly, D is nothing else but GC. So, what is happening? H of AC is FA GC. F, so as if you are applying F on the first part. Think you are applying F on the first part and G on the second part. And that's why we write, since this is unique, we denote this H by F cross G, making our life simple by this equation. F cross G of AC is FA GC. Okay, so that's this number 4. So it's a quick application of number 3 to give you this product function. Okay, and the red thing, can you see a connection between the underlying set of this function and so on? Well, I will ask you to look into it and try to give your understanding. Yes, I would not expect a very clean answer at this stage. Remember, if you function means it's a relation. So actually what you have given me is AC and FA GC, this ordered pair, right? This is your H. Formally speaking, this is your H. Now, well, I want to see you to see whether you can see this as some kind of a Cartesian product and so on and so forth. But that's more of a kind of what should I say? It's a testing question, nothing else. It's a little bit different than the other reds, right? So, yeah, and the moment you see that this function f cross g is the unique function which satisfies this diagram 50, then these two questions should become very clear. Okay, it's already 7:30. I will ask you now to ask me questions, and then to you to settle down on this, and then again, so go through what I have said and try to answer these questions that are here. Did I answer both the questions that we started off with? Somebody said disjoint union, right? Yes. Who was it? I don't remember. Was it Stanley or Ayub?
It was Charles.
Charles, okay. Okay. Shall we take a go at disjoint union, or should we stop here and you would like to have another reading and then we go through disjoint union?
Yeah, that will be fine, Doc.
Okay. Okay.
Let's just regurgitate what we have done, and then maybe in the next lecture, then we can go through that.
Yeah. So next week I would be happy if you could give me a proof of up to 51 and 52. Equations 51 and 52. That means up to 4. Okay?
We'll be looking at 50 and 51. Seemingly, you have already given the equations 3 and 4.
Seemingly, yes. 51 and 52, right?
Okay, so we'll concentrate on those ones.
No. I'm saying up to that. Up to. So, all the questions up to example 5. Up to example 4. So, examples 1, 2, 3, 4 and all that is beginning before that. Is there any question up to that? No. There is no questions up to that. No.
So we proceed to 50 and 51.
So your next assignment would be submission of your answers to questions given in red up to example 4. Okay? Example 1 is the identity function. There is something called proof this there. Example 2, there is nothing. Example 3, I have already given you the proof and everything, but you have to write it down very, very clearly. Right? Example 4 is a probing question. So you look into that set and try to, okay, come up with some kind of an answer. Let me see. I would not be, let me see what you come up with in question 4. But in question 4, there is also this y there, and after equation 50, right? There is this y, and then there is, after equations 51 and 52, there is this proof. Okay, so essentially you have to provide answers to these questions. Next assignment. I mean to say next week, yes. Clear? Yeah.
Okay, Doctor, I want to ask on chapter 1. I'm quite confused on the activities which we used to submit. Then, we are submitting the exercises which are left as the tasks which are left as an exercise.
Yes. Yes.
Okay, all of them.
Yes, all of them.
Okay. I'm clear now. It's for I mean on my UNISA, submission on my UNISA.
Yeah. Okay. You are?
I'm Mavutu.
Is this the first time that you are coming?
No, not the first time. I usually attend the class. It's just that I'm experiencing a network problem most
Okay.
of the time. Sometimes I got lost.
Okay.
Yes.
Okay. All right.
I'm attending all the time.
Okay. Okay, any questions?
All good, Doctor.
It's good now, till yet. Okay.
Yeah, thank you very much, Doctor.
Thank you. We will meet next week.
Thank you.
Thank you.
Thank you very much, Dr. Pasa.
Thank you. Keep well.
Okay. Goodbye.
Goodbye.